Hi everyone, I'm Chris and welcome back to the lecture on neural networks of this machine learning course. In the previous section we learned how to calculate the gradient for a single layer perceptron. But what about neural networks with hidden layers? In this section we will derive the famous backpropagation algorithm. With a backpropagation algorithm, the gradient of the cost function of neural networks with multiple hidden layers can be calculated efficiently. The gradient contains the derivatives of the cost function with respect to every trainable parameter of the neural network in every layer. The idea is to start on the right side with calculating the gradient components of the output layer. We already know how to perform the gradient calculation and the corresponding weight updates. We can use the delta rule of the previous section. To apply the delta rule, we need to calculate the input into this last layer of neurons. This can be easily done with a so-called forward pass. Thereby, the neural network takes the training data and calculates the outputs for all layers for the current values of the weight parameters. We start from the input on the left and calculate all outputs until the cost function value on the right is calculated. The result for the last hidden layer closest to the output are the inputs we need for our delta rule. In the following, we will calculate the gradient components of the hidden layers. We find out that the gradients of the hidden layer depends on the calculations of the gradients of the output layer. So we can reuse the previous gradient calculations of the delta rule. Further, the input for the hidden layer was already calculated by the forward pass. Similarly, we can calculate the gradient components of the next hidden layer. This successive procedure of calculating the derivatives layer by layer, starting from the output layer, and reusing the preceding derivative calculations give the algorithm its name: backpropagation. In the following, we will calculate the gradient of the cost function with respect to the weights in the hidden layer closest to the output layer. At first, let's take a look on the calculations in the neural network. The cost function h depends directly on the output y tilde of the neural network. It sums the squared differences of the capital M outputted components, y tilde m. Note that here we take only a single data point into account. If you want to take more data points into account, an additional summation over the data points needs to be performed in the cost function. The network's output is identical to the output of the last neuron, ym of layer 1. The network's output are the activation functions of the output layer. The activation function of the mth neuron takes the summation Zm of the linear combinations of weights and inputs. We can write this in vector notation. The output vector y superscript 1 with capital M components is equal to the summation vector z superscript 1 when the activation function sigma is applied component by component to the vector z. If we want to express all summations Zm of the output layer in a single vector z superscript 1, we need to sum over all vector components by m of the mth component, highlighted in blue, times the corresponding unit vector EM. Vector EM has a 1 in the mth component and is 0 elsewhere. The summation performed at the mth output neuron, Zm, is the linear combination of the input to this neuron with the multiplicative weights. The input to this neuron are the outputs of the preceding hidden layer neurons. There are capital L neurons in this hidden layer, and the output of the lth neuron is YL of layer 2. This output is multiplied by the weight WLM of layer 1, connecting this output with our mth neuron of the output layer. The sum of all inputs to the output layer YL of layer 2 times the corresponding weights WLM of layer 1 is the summation at the mth neuron of the output layer. This summation starts at L equals 0 to include a bias term W0M of layer 1. Note that by definition Y0 of layer 2 is 1. The output of the lth neuron of the hidden layer is given by the neuron's activation function. So applying this summation vector of this hidden layer, vector d superscript 2, component by component, gives the output vector of this hidden layer, vector y superscript 2. The summation vector depends on the weight parameters of this hidden layer. So vector z superscript 2 is equal to the sum over all neurons of this hidden layer by L to account for all summation components, and the sum over all inputs to this hidden layer by K of the connecting weights WKL of layer 2 times the input to this hidden layer Vk times the unit vector EL. The input to this layer Vk can be either the input to the neural network, then Vk equals xk, the cased input variable, or the layer input can be the output of another hidden layer. This hidden layer would then be labeled with a superscript 3. This is because we used 1 for the output layer and 2 for the hidden layer closest to the output. The output of this layer number 3 is then yk, indexed with a superscript 3, and can be used as input vk. We want to calculate the derivative of the cost function h with respect to a weight wkl of the hidden layer number 2. Therefore, we apply the chain rule according to the dependencies explained before. These dependencies are displayed again on the right side. The cost function depends on the neural network's output. This output is calculated by an activation function. The activation function takes the linear summations, and so on. The gradient decomposes into 5 terms according to chain rule. In the following, we will calculate each of these terms step by step. First, we calculate the first term on the left according to the decomposition with the chain rule. This is the derivative of the cost function with respect to the outputs of the output layer, vector y superscript 1. This is equal to the output of the neural network. We rewrite the gradient, which is a row vector, by using the sum representation. The gradient is the sum over all components by m' of the gradient's component times the corresponding row unit vector. A gradient's component is the partial derivative of the cost function with respect to ym' of layer number 1. Similar to the calculations for the delta rule, we use the mean squared error as cost function with the squared differences of output and data. The derivative of a summand in the summation gives 2 times the difference of model output and data times the derivative of the inside. The factor 2 cancels with a factor 1/2. The derivative of the inside gives the derivative of ym of layer 1 with respect to ym' of layer 1. This is because ym is a constant value, the data point's target value. This derivative is only non-zero if the component m equals m'. This can be represented by the so-called Kronecker delta, delta m'. This Kronecker delta is 1 if m equals m', and otherwise it is 0. So the two summations reduce to a single one over m of the difference between model and data times the unit vector em transpose. This is a row vector of the difference of model output and data. Next, we calculate the second term on the left according to the chain rule. These are the derivatives of the output vector y superscript 1 with respect to the summations in this layer vector z superscript 1. We express both vectors by the summation over the components times the corresponding unit vector. The summation in the numerator has column unit vectors. The summation in the denominator has row unit vectors, so transposed unit vectors. Both summations are written using different summation indices m and m', so we can mix the summation terms. Thus, we place both summations in front, and we have the sum over m' and m of the partial derivative of ym of layer 1 with respect to the m' of layer 1 times the unit vector em times the unit vector em' transpose. For the calculations we consider the sigmoid activation, but the calculations for different activation are similar. We already calculated the derivative of the sigmoid activation function previously, for example for the delta rule. The derivative of the network's output of the mth neuron ym of layer 1 with respect to the m' of layer 1 was ym of layer 1 times 1 minus ym of layer 1 times the Kronecker delta delta m'. The Kronecker delta accounts for that there is only a non-vanishing derivative if m equals m'. Substituting this into the expression on the left side, it follows that the derivative of the neuron's output, vector y of layer 1 with respect to the summation vector v of layer 1, is the sum over m and m' of ym of layer 1 times 1 minus ym of layer 1 times the Kronecker delta m' times the two unit vectors em and em' transpose. The Kronecker delta m' reduces the summations because it is only non-zero for m equals m'. Here we choose m as remaining summation index. Next, we calculate the term in the middle according to chain rule. The derivative of the summation vector z of the output layer with respect to the output vector y of the hidden layer. Again, we represent both vectors by their sum representation. The expression for the column vector d of layer number 1 can be seen on the right side. The representation of the gradient with respect to the vector y of layer 2 is a sum over all components by L' of the derivative with respect to yL' of layer 2 times the corresponding transposed unit vector EL'. We used different indices for the summations, so we can place the sums in front and the unit vectors behind the derivatives. The partial derivative of yL of layer 2 with respect to yL' of layer 2 is 1 for L equals L', otherwise it is 0. This is again a Kronecker delta, delta LL', which is 1 for L equals L' and 0 otherwise. This reduces the summations over L and L' to a single one. Here we choose the index L. This gives us the sum over L and M of the weights of the output layer WLM of layer 1 times the unit vector EM times the unit vector EL transpose. Next, the fourth term is calculated. This is the derivative of the output vector of the hidden layer, vector y superscript 2, with respect to the summation vector of this layer, vector v superscript 2. We express both vectors by their sum representation using different summation indices. For the column vector y superscript 2, we have the sum over all neurons in the hidden layer by L of the output of the else neuron yL times the else unit vector. The gradient is expressed as row vector by using summation of the neurons as components with a unit vector transpose. The summations are placed in front. This gives the sum over L and L' of the partial derivative of yL of layer 2 with respect to the L' of layer 2 times the unit vector EL times the unit vector EL' transpose. In this neuron layer, we use again the sigmoid activation function applied to the summations. Substituting its derivative into the expression above yields the sum over L and L' of yL of layer 2 times 1 minus yL of layer 2 times the Kronecker delta LL' times the unit vector EL times the unit vector EL' transpose. The Kronecker delta from the derivative reduces the two summations. So the derivative of the output vector of the hidden layer with respect to the summation vector of the hidden layer is the sum over all neurons of yL of layer 2 times 1 minus yL of layer 2 times the unit vector EL times the unit vector EL transpose. Finally, the last term, the derivative of the summation vector of the hidden layer with respect to a weight WKL of this hidden layer, is calculated. The summation vector uses linear combinations of the inputs into this layer. The inputs are denoted by Vk. On the right side, the corresponding calculations of the neural network are reconsidered. The expression depends directly on the weight parameters WKL of the hidden layer number 2. We use new indices when we substitute the summation vector into the derivative calculation. Then we can place the summations in front. Of course, we know that there's only a non-vanishing contribution if k' equals k and L' equals L. Then the expression reduces to vk times the unit vector el. This is because the weight wkl connects the cased input to the else neuron of the hidden layer. Thereby, wkl scales the input vk linearly. The contribution to the summation at the else neuron is wkl times vk. The derivative with respect to wkl gives vk. Now we can put everything together. On the left side, the expression of the cost function derivative with respect to the hidden layer weight wkl is shown. According to the chain rule, it has 5 contributions. The results calculated are summarized and can be substituted into the cost function derivative. The result is shown on the right. Here, each substitution has its own summation indices different from the others. Then we can mix the multiplications. There are a lot of unit vectors and summations. The multiplication of a unit vector E transpose, which is a row vector, times a following unit vector E, has only a non-vanishing contribution if the one in both vectors is in the same component. For example, the unit vector EM transpose times the unit vector EM prime is 1 for m equals m prime and 0 otherwise. So this is a Kronecker delta mm prime. As you can see, we can choose pairwise subsequent vectors and obtain several Kronecker deltas. We see that m equals m prime and m prime equals m double prime. So we have m equals m prime equals m double prime. Similarly, we have L prime equals L double prime and L double prime equals L, so that L equals L prime equals L double prime. We have summations over L prime and L double prime, which both collapse, and L prime is L and L double prime is L as well. Here again our result is displayed. The result gives the derivative of the cost function with respect to the weight parameter wkl of the hidden layer. In the expression, there's a single summation index m over all output neurons. Further, there are 2 open indices, k and l, which correspond to the weight wkl, for which we want to calculate the derivative. This expression depends on the output values of the hidden layer as well as on the output layer. These values are calculated by the forward pass. The forward pass calculates all layer outputs for the neural network with the current weight parameters. Note that vk can be an output of a preceding hidden layer. Then it is determined by the forward pass as well. Elsewise, it can be the input to the neural network. Then, vk is the cased input variable xk. Further, our expression depends on the target values ym of the data point. The expression also depends on the values of the current weight parameters. The result for the derivative can then be used in a gradient-based minimization, similar to the delta rule. When we take a closer look on the expression for the cost function derivative, we see that the first part is equivalent to the delta rule contribution of the output layer. This was denoted by delta M sigmoid. So we can reuse the results for the gradient of the output layer to calculate the gradient of the hidden layer. Consequently, first, the gradient of the output layer is calculated. Then, the gradient of the hidden layer closest to the output is calculated. After that, the second next hidden layer to the output is calculated, and so on. This backpropagating approach, calculating the derivative from the output layer toward the input layer, is very computational efficient because we can reuse the previous calculation results. This algorithm is called backpropagation. Section finished. If you like this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.